This is a breakthrough, a new way towards extending context window a lot, maybe even to 50, 100 million tokens instead of just 1 million right now. In this video, I want to do some research myself and I want to just document what I do. So this has transformer heads and Mamba heads. Transformer heads are quadratic scaling and they cover entire sequence length, take information from entire sequence length, and Mamba heads are linear scaling. They're similar to recurrent neural networks, but they can be parallelized. And so we can make them run fast on GPUs. This could allow very, very long reasoning. Eventually, like this could be the dream, but trillion token context window and billion token of reasoning. And it's very, very fast, a lot faster than this. It's like instant entire book of reasoning and maths. So this could be the next big thing for LLMs and LLM architecture that's a lot better. Finally, solving problems with quadratic complexity of transformers and LLMs. And then we can also use DeepSeek's native sparse attention for even longer, for the attention heads that we use, make them a lot longer, take a lot more tokens. This could be the future of researching LLMs, and I like LLMs unlike other people who complain about LLMs. The reason I like them is they're very useful at coding, and we just need to improve them a little bit. Maybe this research, well, we are close, and this research, we are very close, and we can make them so much better, reasons for so much longer, so much faster. So we are very close to something very great that then we can use to code fast other AI research to invent better mechanisms and have huge context window, huge amount of reasoning very fast instantly. So now I'm gonna be implementing this paper. So I have my own transformer LLM and I'm gonna be trying to add Mamba heads. Let's create a new repository, transformer Mamba LLM research. I'm just gonna take these templates, Python and MIT license, and create. Clone it to my PC and open it in Cursor. I have my own classic transformer large language model that you can find in my video, publish your own LLM, build and train your own LLM. So I'm gonna copy that here, and then I'm gonna take code from NVIDIA, modeling Nemotron age, and then I'm gonna just maybe make another file, Nemotron, sorry. Then I also wanna copy this actual model, Nemotron Nano 2, that I want to actually implement. So I copied this whole code, put it into Opus and said, explain the architecture of this model in detail. I will code it, so explain it in detail, focus on Mamba parts. I copied this text, not code, sorry. So it finished, it explained a bunch of architecture from the paper. So it's gonna diverge a little bit from the previous Nemotron age paper, but it doesn't matter. Let's go here, I copied that. I gave it this prompt. Let me show you. My LLM is in transformer LLM Pi. I need to implement hybrid transformer architecture in it instead with Mamba 2. Check Nemotron Pi and this description above. Adapt model size to my model, etc. And I'm just gonna send it. Let Claude Sonnet work on it now. It implemented changes. Now let's see what changes it implemented. There is a lot of new code, as I can see. The new changes are extended model config for hybrid architecture. So we have this hybrid layers bool equals to true and number of layers 12 increased from 6 for hybrid architecture. We had 6 layers before. Then we have Mamba 2 specific parameters scaled down from Nemotron. We want to build a bit smaller model. Mamba number of heads 6, head dimension 64. I think this is same. Yeah, these two are same. State size 64 reduced from 128. Number of groups 2 reduced from 8. So this is the main reduction because we don't want a 9 billion parameter model. We want maybe 1 billion, less than 1 billion, or a bit more than 1 billion. Mamba convolutional kernel 4. And expansion 2. I'm not actually sure 100% about Mamba architecture. I know well transformer, but not Mamba, but I think it must be like similar. It's all neural networks, this kind of stuff. Implemented core Mamba 2 components, selective scan algorithm, selective scan naive but correct implementation of Mamba's core selective scan, processes sequences with linear O of L complexity versus attention square complexity. Quadratic, I should say. Mamba 2 mixer class, input projections, X projection, Z projection for gating, state, selective state, I forgot what this is, SSM parameter projections. We have causal convolution, 1D conv with kernel size 4 for local context. Actually, my idea is to use native sparse attention by DeepSeek, so it's gonna work well for long attention, and for that we can maybe even use raw bytes as input and not tokens, but also we could use tokens and have like 50 million token context window or something. We'll see. Sam Altman said that the dream is like a trillion token context window and it lets it reason for like long time. It also added grouped query attention, which, okay. I don't know where it added it. Should have added it to this scale.product attention then. Here we see entire class, grouped query attention implemented. I think the implementation seems correct. I just don't know why I didn't use PyTorch as native, like the thing. This scale.product attention. This can also do grouped query attention. And it's probably better optimized because PyTorch optimizes it into oblivion. Looks like we just have one attention layer. So our structure of 12 layers is Mamba feed forward, Mamba feed forward, Mamba feed forward, attention feed forward, and then Mamba feed forward, Mamba feed forward. So Mamba 2 layers, 6 in total, handle long-range dependencies with OL complexity. I'm not sure if they can actually handle long-range complex dependencies. I think they can, like, the closer the thing is to the current token, the better it's represented here, maybe. And this attention is what actually handles the long-range positions and dependencies. And then it changed feed-forward layers from SILU to squared ReLU, like in Nemotron. So towards square ReLU, and then pass in the linear weights and X as input. So Mamba has no positional embeddings. It handles position through convolution. So we have separate embedding and output layers. It's not tied anymore like in the original, where you have the dictionary of tokens and embedding tokens in the beginning of the LLM transformer, and the output head in the end. Dictionary across all of the tokens is the same matrix, but now it's not same anymore. A special Mamba initialization marks A log and D as no weight decay. Not sure what this is. Architecture flexibility falls back to pure transformer if hybrid layers is false. So this is better for long sequences because of this O of L linear complexity in most of the parts. Faster inference, especially for generation tasks. So this could even mean faster reasoning, but we need to figure out what we want to do here. This is promising. We need to research. As I said, there are many ways to build intelligence. It's not just like one way, transformer, something. We need to discover the single way. There are probably many ways, and we can do it in any way we want. Now I will run it on Novita AI. I'm just gonna rent a very cheap GPU, 4090, very good GPU for just $18 per cent. It's 50% off. Link below, and you just need to choose spot billing. Make sure to install datasets and transformers. Now I see that the tokenizer is being downloaded. I don't see any errors, but I do expect to be a couple errors when running this for the first time. So then I'm just gonna send it to Cursor. It's gonna fix it. There is some issue. So the error was caused by trying to expand the tensor 6 to shape 664 directly. I need to add 2 unsqueeze operations to make it 611 first, then expand to 664. Here we see A is equal to A.unsqueeze.unsqueeze and then expand. And then self number heads, head dimension, state size. So those will be 64 as I'm guessing. I recommend you do some exercises with unsqueeze if you don't know what it does in Google Colab, for example. Just ask ChatGPT to give you some exercises, use the learn mode to get intuition, how expanding this dimension, what it means. I could open this file remotely, but I do it on my PC, And then I just pull on Novita's GPU because I don't want to set up GitHub, although that's also easy, so whatever, you can do it anyway. And then I run it again. Our model has 48 million parameters, which is good just for testing a little bit. Now we actually ran out of memory. So we have this naive selective scan implementation, which I'm not sure what it is, but we'll see what we change. And we will reduce batch size. So we reduced number of heads. We reduced dimension. This is not good. This should be power of 2. I don't like this. Mamba state size 32, that's okay. I think I'll just return this maybe to 64. Batch size 16 instead of 24. We fixed out a memory issue, but now there is some other bug. So to continue, memory efficient selective scan. Chunked processing, process 32 tokens at a time instead of all at once. This is too few maybe. In place operations, use mul and add to avoid creating new tensors. Periodic memory cleaning with torch CUDA empty cache between chunks. Pre-computed expansions, avoid repeated tensor expansions. Reuse tensors, minimize temporary tensor creation. So now we got from around 148 megabytes per batch, we got to 24 megabytes per batch. The error occurred just because of these in-place operations, and it modified tensors needed for gradient computation. So it replaced them with regular computations that preserve gradient graph. Computational graph, I should say. The training seems very slow, but we'll fix it. So PyTorch's AutoGrad tracks computational graphs to compute gradients. In-place operations modify tensors that are part of the graph. This breaks the chain of gradient computation during backpropagation because so the value is part of the graph, but when you modify it in place, then it changes that which it shouldn't. I also see the issue here. Is Mamba not parallel? Can it not train parallelly? Why is it so slow? So there is just 20% GPU utilization, 50% memory, so 14% compute. I don't know why it's so slow though. So there is a fundamental architecture difference between Mamba and Transformer when it comes to parallelization and the trade-offs. During training, Mamba 2 uses a parallel scan algorithm that enables parallelization. The key insight is that SSM recurrence can be reformulated as an associative scan operation which is parallelizable on GPUs. This is why training is efficient. Inference, the sequential bottleneck. During autoregressive inference, generating tokens one by one, Mamba becomes sequential, which is okay. That's okay. We just want fast parallel training. And I think we also want sequential inference. That's gonna be sequential anyways. So Mamba is really good for reasoning traces because it's like long output. I want Opus to explain step by step how to parallelize Mamba in training. Then I'm gonna give it to Sonnet to implement it because I think we don't have it. 4 hours for 5,000 steps. Usually it would be like a few minutes, maybe 4 minutes, not 4 hours, if it was pure transformer. Okay, while it's generating, let's try to understand what it's actually writing. Understand the sequential problem. First, let's see why naive Mamba appears sequential. For each time step t, we need to get the t minus 1, so it depends on the previous time step. We have this 4t in range sequence length. Is dependent on the sequence. Step 2, reformulate as associative scan. The key insight, we can reformulate the recurrence as a scan operation with associative operators. Seeing this for the first time, it's a bit tough, but the way I understand it is you just multiply all of the tokens from the beginning. There is a better explanation, but let's just first see. I told it to implement this, and it says that it previously did not have parallel training implementation, so now it implemented it. The fundamental challenge. Traditional RNNs suffer from fundamental limitation. Each hidden state depends on the previous one, creating a sequential bottleneck. So you can't compute current hidden state without the previous hidden state. And Mamba's state space model has the same apparent problem. It also depends on the previous state. But check this out. Let's say we are adding 7 numbers naively. So we add these two, then this, so it's sequential. But addition is associative, so you can add first two together, and second two together, third two together. And then add these two groups, and then add all at once. So there is parallelization right there. This is the principle behind parallel prefix sum, reducing O of n steps, sequential steps, to O log of n. And that's an absolutely crazy speed up. You see, you can increase x as much as you want, but the time necessary to compute it is almost the same after some point. So log of n is almost the same as you increase the n. Look how O of n grows much more than log of n, which actually just plateaus at some point. So this is a drawing of how Mamba works. So they divide this sequence into operators. So then the same principle, you do 2 operators in parallel. So these operators give this one, these give this one. Each level can be computed entirely in parallel. We've reduced 8 sequential steps to 3 parallel steps. So from here we go 1, 2, 3. Sonnet is struggling to implement parallel function, so I actually just copied the code to Opus and it gave instructions, so I'm gonna give it back to Sonnet. This issue persists. It's just not able to implement parallel training. Next video we will just go ahead and learn simple step-by-step Mamba to implement simple version of it manually and do parallel training. So we will understand that and then we will go back to this one. So see you in the next video.